Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about counting and probability. We're going to start with the fundamental counting principle. We'll also discuss the pigeonhole principle, and then permutations and combinations. After that, we'll get into probability. We begin with the fundamental counting principle. Sometimes called the product rule of counting. And it goes like this. If you have two tasks, and there are n ways to do the first task and m ways to do the second, then there are n times m ways to do both. For example, suppose we have a coin flip and a die roll. For the coin flip, there are two outcomes, two ways to fill this slot. For the die roll, there are 6 outcomes, 6 ways to fill the second slot. So the total number of possible outcomes is 2 times 6, or 12. As another example, let's suppose that you have outfits where your shirts are red, green, or blue, and your pants are either khaki or blue jeans. How many possible outfit combinations are there? You can see that there are 3 different shirts and 2 different pants. So you have 6 conceivable combinations. As another example, I'm going to ask, how many ways can 2 playing cards be drawn from a deck? So there are 2 slots to fill. Well, let's suppose that this deck has 52 cards. Then there are 52 ways to fill this first slot. But the second slot has only 51 ways because you've already filled the first slot with one of the cards. There's only 51 ways to fill the second slot. So the total is 2,652. There are 2,652 ways that you can choose 2 cards from a playing deck. One thing we should be careful about is this treats say card A and then card B distinct from card B and then card A. So if you don't distinguish between the order in which the cards are received, then you'd have to divide this number by 2. As an adjunct to the last problem, how many ways to take 4 cards from a deck? Yes, this fundamental counting principle generalizes to where you have as many slots to fill as you'd like. That'd be 52 times 51 times 50 times 49. And that's 6,497,400. But keep in mind that order is important here. So getting 4 aces, there are different ways of getting 4 aces. In fact, if you're filling 4 slots with aces, there's 4 ways to fill the first slot, 3 ways to fill the second, 2 ways to fill the third, and 1 way to fill the last. So the number of different kinds of combinations of all 4 aces being drawn would be 24. So if you want to discount those rearrangements, you're going to have to divide by the number 24. As another example, how many ways can you roll 2 dice? And the answer is, of course, 6 times 6. There are 2 spots. So there are 36. Let's enumerate these to make it very clear what those 36 possibilities are. Let's write these as ordered pairs. You can get a 1 and a 1, a 1 and a 2, a 1 and a 3, 1 and a 4, 1 and a 5, and a 1 and a 6. Then you can get a 2 and a 1, a 2 and a 2. Notice a 2 and a 1 is distinct from a 1 and a 2 by this enumeration. We can keep going until we get to 6 and a 1, 6 and a 2, and 6 and a 6. So there are 6 rows and 6 columns, and so there's a total of 36, or 6 times 6, possible outcomes. But again, a 1 and a 6 is the same as a 6 and a 1 in some people's minds. So we'll have to figure out a way to eliminate those duplications at some point. But for now, you have n ways to fill the first column and m ways to fill the second column, so you get n times m ways to fill both of those. Here's another classic example. How many bit strings are there of length 8? So we have 8 slots. Each slot is filled with a bit, and a bit either takes on the value of 0 or 1, so there are 2 possible ways to fill that first slot. 2 possible ways for the second, 2, 2, 2, 2, 2, and 2. That's 8 2s, 2 to the 8. That's 256. A bit string of length 8 is sometimes known as a byte, and bytes, and the total number of bytes then that are possible are 256. There are 256 possible values for each byte. How many license plates, car license plates, are there consisting of 3 letters and 4 and 4 numbers, digits? So for letters, you have 26 ways of filling each slot. But for the digits, there are 10 ways of filling each slot, 0 through 9. And so the total is 175,300,000 760,000 different potential plates. This, of course, ignores the fact that many of these letter combinations will be considered risque and hence be banned from the list. But nonetheless, if we don't do that, we have 175 million. How many functions are there from a set of n elements into a set of m elements? They're n domain elements, and to each of those domain elements we need to assign one of the range elements. So we're going to have n slots, and each of those slots can be filled with m different possibilities. So we get m to the power of n, number of different functions from a set of n elements to a set of m elements. We next consider counting one-to-one functions from a collection of n elements into a collection of m elements. Here you must have m is bigger than or equal to n, otherwise there's no such function. So again, you have n places, but to make this one-to-one, you can't have different domain places that yield the same range outcome. So while you may have m ways to fill the first slot, there's only n minus 1 ways to fill the second slot, and m minus 2 ways, all the way down to m minus n minus 1. It's n minus 1 because you started with m minus 0. 0 through there. So to get n possibilities, you have to subtract up to n minus 1. We next describe something called the sum rule. If a task can be done in n1 ways or in n2 ways, suppose there are two categories of ways of accomplishing a particular task, where these have nothing in common, then the task may be done in n1 plus n2 ways. In our next example, suppose that a student wants to take either literature or English composition, but not both. Let's suppose that amongst the literature classes there are 6 choices, and amongst the composition classes there are 2 choices. How many total choices does this student have if the student is going to take one of these or the other? And the answer is 8. The student has 8 choices. In the last formula, we had 2 different ways of doing things with no ways in common. But what if these ways do have something in common? Suppose we have the number of ways of accomplishing a task and then another number of ways of accomplishing a task, but they overlap. How many total ways are there to do this? We get something called the subtraction rule. So if a task can be done in one ways or in two ways, but there are m ways in common, then the total number of ways is, well, let's suppose you have n1 over here and n2 over here. The problem being is that if you add n1 and n2, you've added the ways in common twice, once for A and once for B. So to account for that double counting, you have to subtract off m, the number of common ways, to get the total. This is just an extension of the way in which we counted the cardinality of sets. Cardinality of A plus cardinality of B double counts the intersection, so you have to subtract out those common to both to get the total cardinality of the two. That's the cardinality of A union B. In our next example, suppose 350 applications from college grads arrive for a new position of these. 220 majored in computer science. 147 majored in business. And 51 majored in both. How many majored in neither? We'll first count how many majored in either computer science or business. And to do that, we take our 220 and add the 147, but we have to subtract those that were in both. Let's see, 47 minus 51 is 96. If you add that to 220, you get 316. So to get the total number who majored in neither of these two things, we take the total number of applicants and we subtract out the 316. That gives us 34 were majored neither in computer science nor in business. We next turn to something called the Pigeonhole principle. And to illustrate the pigeonhole principle, suppose we have 5 pigeonholes. These are places where a pigeon will roost. If there are 6 pigeons, and all fly into a pigeonhole, then you can safely deduce that at least one of the holes has 2 pigeons or more. Then at least one pigeonhole has 2 pigeons. So the way that we are stating the pigeonhole principle is if there are n pigeons and k less than n pigeonholes, at least one pigeonhole has at least two pigeons. This statement is slightly more general than the way we stated it with this specific example. A similar pigeonhole principle is that if you have n pigeonholes and n pigeons, and if each pigeonhole has at least one pigeon, but all but one of the pigeons have already filled a hole, then the last remaining pigeon must go in the last remaining hole. Here's another example. Suppose f is a function mapping a set x into a set y, and the cardinality of x is n, but the cardinality of y is k strictly less than n. So basically you have n pigeons but k holes, and k is less than n. Then some of these holes are going to have to be doubled up. There's going to be more than one domain element that goes to the same range element. When that happens, we say that f is not one-to-one. So there exist x1 and x2 in the domain such that they output the same thing. So it's not one-to-one. The generalized pigeonhole principle goes like this. F is mapping x into y. Cardinality of x is n. Cardinality of y is m. And suppose k is the ceiling function of n divided by m. Then there exists k elements, x1, x2 through xk within x, such that f of x1 will be f of x2, and that'll equal f of xk. The proof of the generalized pigeonhole principle is by way of contradiction. Yes, suppose x has size n, cardinality of y is m, and there does not exist k elements such that f of x1 equals all the way to f of xk. There does not exist any such set of elements. Then there are at most k minus 1 elements having a common function value. That means there are at most k minus 1 elements of x such that f of x equals y1. So no more than k values of x that equal y1. Let's suppose y is enumerated as y1, y2 through ym. What is more, there's at most k elements so that f of x equals y2, and so on. So for each of these m outputs, there are k minus 1 inputs. We have these two slots. M outputs, k minus 1 inputs. If all of the inputs are different, then there are this many at most domain elements. If all of these different x's are distinct, which I guess they have to be if we're dealing with a function, then you have at most this many domain elements. But wait a minute, m times k minus 1 is less than m times n divided by m, and that's n. Well, that's a contradiction because we have n domain elements. And therefore, there must be at least one element which has k distinct domain elements having a common y value. We now discuss permutations and combinations. First of all, a permutation is a reordering of objects. For example, suppose I have 1, 2, and 3. There are a number of different permutations of these. We could have 1, 3, and 2, 3, 2, and 1, etc. We'll talk about how to count the number of permutations in a minute. The number of permutations of k objects selected from a set of n objects is denoted by n permute k, or the permutation of n objects taken k at a time, and it is equal to n factorial divided by n minus k factorial. As an example, how many ways can we select, let's say, president and vice president from a group of 4 people? So you have 4 people to choose from and 2 slots. The fundamental counting principle would say 4 ways to fill the first slot, and then 3 ways to fill the second, or 12. But we can also calculate this using our formula, 4 permute. That's 4 factorial over 4 minus 2 factorial. 4 factorial is 24. 4 minus 2 is 2. 2 factorial is 2. And so the answer is 12. Let's look at some specific examples. If I have n permute n, that's n factorial over n minus n factorial. That's 0 factorial, and 0 factorial is, by definition, 1. So if you have n objects and you're counting the number of permutations of those n, all of the n, there are going to be n factorial ways of doing that. You can also arrive at this number by the fundamental counting principle. What if I have n permute 0? That's n factorial over n minus 0 factorial, or n factorial over n factorial, which is 1. So there's only one way to select no objects from a collection of n, and that's by collecting no objects. Permutations count the total number of rearrangements. But let's suppose that order is not important. Then we end up with something called combinations. And we're going to have n choose k, or the combination n objects chosen k at a time. And this is going to be where order, the rearrangements, is not important. And it turns out n choose k has the formula n factorial over n minus k factorial times k factorial. How do you get the extra factor of k factorial in the denominator? The number of rearrangements of k items taken k at a time is k factorial. So if you divide out by the number of equivalent rearrangements, you'll have to divide out by k factorial. And so this is the way to calculate the number of different choices, k objects taken from a set of n, where the order is not important. You use combinations. As an example, how many 4-card hands can be drawn from a deck of 52? We'll assume here that the order in which the cards are chosen is not important. So we'll have 52 combine 4. That's 52 factorial over 52 minus 4 factorial times 4 factorial. 52 minus 4 is 48. 48 factorial. But think about how 52 factorial and 48 factorial can cancel. 52 factorial is 52 times 51 times 50 times 49 times 48, 3, 2, and 1. 48 factorial is 48 times 3 times 2 times 1. And then we have this 4 factorial, which is 4 times 3 times 2 times 1, which is 24. All of those cancel with all of those. So we reduce this to just 52 times 51 times 50 times 49 divided by 24. The total is 270,725. So there are 270,725 4-card hands drawn from a deck of 52. There's only one way to get all 4 aces if the order in which you draw them is unimportant, and that is to have all 4 aces. So you can see the odds of drawing all 4 aces in a row is 1 in 270,725. In our next example, suppose a department has 20 professors and will form a 3-person committee. How many possible such committees are there? Well, the answer is 20 combine 3. 20 choose 3. That's 20 factorial divided by 17 factorial times 3 factorial. 20 factorial divided by 17 factorial is 20 times 19 times 18. And 3 factorial, it's 3 times 2 times 1. That's 6. 6 goes into 18 3 times. So you end up with 20 times 19 times 3. And that's 1,140 conceivable possible committees of 3 people that can be drawn from a collection of 20 professors. How many 8-bit strings contain exactly 4 ones? Well, you have 8 slots, but you're going to choose 4 of them. And it doesn't matter what order you choose them, just that you choose the same 4. So it should be 8 choose 4, which is 8 factorial divided by 4 factorial 4 factorial. 8 factorial divided by 4 factorial is 8 times 7 times 6 times 5, and 4 factorial is 4 times 3 times 2. 2 times 4 is 8, 3 goes into 6 twice. So it looks like you have 10 times 7, or there's 70 different 8-bit strings that have exactly 4 ones.